We're going to do examples illustrating the regioselectivity of hydrohalogenation reactions. So we will be adding H and X across the double bond. And that marker didn't go so well. So I'm going to write over here. Okay, we're adding this across the double bond. And what we learned before in a previous video is that that happens with Markovnikov. The chemists study that. We call that Markovnikov regioselectivity. And that is we're adding the H at the least substituted carbon and the X at the more substituted. So let's work a couple of structures here. If we add here any, say, hydrochloric hydrobromine, but just say HX. So what that is we have a first step. Again, this is a proton transfer step. So pi electrons are going to get that proton, and those electrons are going to be now assigned to the X. And in Markovnikov, remember, we're adding the H at the least substituted, and we were forming here a tertiary carbocation. And in the second step, what we're doing is we're having the nucleophilic attack. So now I have X, and this is going to be attacking, and your final product is now this. Now, one more example of that. Let's do this molecule X, and let's do that. Now, let's see what happens. Say that I'm doing hydrobromic acid with that. So again, our first step is a proton transfer. So pi electrons are going to be acting as their base. And what are we forming is the more stable carbocation. In other words, notice that the substitution at the two carbons are different, vinylic carbon. This is a tri-substituted alkene, meaning that we have two substituents at this carbon and one here. The other is on H. The alkene above is, if you notice the substitution at this carbon, we have vinylic carbon, two substituents. In this, you have a hydrogen. So that is also tri-substituted. So that's right. So two substituents here, and here in this carbon, we have, here you had an H. Okay, so now looking at what's attached again, here's H chain, here chain, metal. So it's tri-substituted. And so we're following the same rules. So we're gonna attach the H at the least substituted, so H here, because that way, remember, we form the more stable carbocation. If we did the opposite, we will form a secondary. If we added the H here, we will be forming a secondary carbocation. So this is what Markovnikov rule says, again, thinking in the stability of the carbocation. And then the second step is a nucleophilic attack. In this case, my nucleophile was bromide, again, negative charge. And so proton transfer, nucleophilic attack. So in the final product, we'll have them, let's draw it down here, a bromine. Notice that all carbocations are trigonoplanar geometry about the center, but we're not creating a cutoff center. If those constituents were different, then we need to pay attention to the stereochemistry of the product, because the nucleophilic attack can happen from both sides of the plane. We're going to do other examples doing that.